Are you a dodo bird? No, I am not. Okay, so what we're going to look at in this video here is we're going to go back and check out some more projectile motion concepts. In our last video, we talked about how the x velocity is constant in a projectile problem, and the y velocity is varying due to the acceleration of gravity. But we're going to see what will that cause when we look at objects actually moving in these kind of projectile motion scenarios and in these type of problems. So one of the first things that we might notice is that if we have a projectile motion, and let's just take our cannon here, let's just shove it to 60 degrees and fire it off at 10. Fire! You know, it goes this far. One of the first things we might notice is that the path of this, assuming there's no air resistance, is a nice parabola. And that's just a standard trajectory. We're going to see a lot of parabolas in this. They're going to be symmetric around the center, so it will take the same amount of time to go up as it goes down. And the max height is half of the displacement in the x direction as it is from the max height to the end. So we just get a nice parabola out of this. Okay. Now there are some other interesting things that we're going to see here. We're also going to see that if we are sitting at 60 degrees, if we shoot this at another angle, we can actually hit the exact same spot. And it turns out that that angle we want to shoot at is the complementary angle to 60 degrees. And what we mean by complementary angle is that if we take 60 plus this other angle, it's going to equal 90 degrees here. So 60 plus 30 equals 90, and if we fire the cannon, pew, it winds up at the same spot. Okay. The interesting thing is at 30 degrees, it gets there a lot faster. Okay. 60 degrees will get there to the same position, but you have to go up, and then you have to come down, and that takes time. Where the 30 degrees is just thump, and we get there. Okay. But complementary angles will take you to the same position. This also makes sense because if you shot something directly upward at 90 degrees, you know, you're going directly up and down, you're going to shoot it up and it's going to come right back into the cannon. And if you shot something at 0 degrees, it's never going to get off the ground. So you're going to have the object sitting at the same spot. Okay, so complementary angles produce equal ranges, and that is how far these objects go out. Now traditionally, the greatest range, you know, if you wanted to shoot or throw something the farthest, we do that at 45 degrees. And if we take a look at this here, 45 degrees, fire, we'll send this a little bit further. And if we come back to 40 degrees, it's not going to go as far. It's almost, but it's just not quite. And if we send this up to 50 degrees, we know 50 and 40 are going to be complementary angles. So we're going to, you know, hit just short of the 45. Okay. Now, 45 degrees produces the maximum range without air resistance. Without air resistance, 45 will produce the maximum range. If you include air resistance, this changes. This changes drastically. If you include air resistance, 45 won't actually give you the max range. And the reason why it won't give you the max range is because you're spending too much time in the air. You know, if you have air resistance, then, you know, as the object is moving forward, it's slowing down due to this drag pushing back on it. And as it's like falling down, it's also going through this air and experiencing this drag force. So you're always losing your speed there. So with air resistance, what you actually want to do is you actually want to try to cut through the air more horizontal than vertical, because if you cut through the air horizontally, you're going to gain this range distance before you start losing a lot of that speed. You want to try to gain that distance before your speed dies out. So if we take a look at this here, we'll just set this to 45 degrees. We'll turn air resistance on, and you know, we'll just fire this thing off to see what happens here. Okay, so here, let's fire this at like let's fire this fast at 30 degrees. Ready? Or 30 meters per second. Fire, boom. That's what we get. If we put this down a little bit, let's just shoot 30, we should get a little bit further. Bang. And if we zoom back into that, yeah, we see once again the 30 lands far. Notice how it came out really fast and then it slowed down, and the 45 here, it's actually going to land short. And that's simply because if you notice with air resistance, our shapes aren't parabolas anymore. It kind of starts off parabolic, but then as we've slowed down, the back edge of this kind of squeezes together. Okay, so that's kind of a weird thing we see there. If we remove air resistance, so let's get rid of air resistance again. We don't like it. It makes everything difficult because of how it smushes these parabolas together. If we remove air resistance though, and we shoot an object off, let's set it back to 30. It's going to get to here, which is, how far is this? 8.83 meters, give or take a little bit due to the rounding of the computer, okay? If I double the speed from 10 to 20 and I keep the angle the same, maybe it'll go twice as far. So instead of winding up here, maybe it'll go out here, like just beyond the 15 meter mark. Maybe it'll hit like 16 or 17. And if we fire this, fire! We see it went way farther. If we actually zoom out and take a gander, we see this went to 35.31. That's like not 2 times as far, that's 4 times as far. And if we speed this up to 30 meters per second, it's not going to go 3 times as far, but it's going to go way further out there. It's actually going 9 times as far. It's going all the way out to like, just under 80 meters here. It's also going 4 times as high and then 9 times as high as the original. And that's because our ranges and our max heights, they're not doubled as we increase the velocity. They are squared with the increase of velocity. So if we double the velocity, if you take your velocity and you say, hey, I've just doubled it, well, 2 times that velocity squared is 4. And if you've tripled it, 3 squared is 9. And if you went 4 times as much, you went 16 times as far and 16 times as high. So increasing your velocity a little bit will actually give you a square ratio in which you move out from that. So that's something to keep in mind as well. It's the squares that matter, okay? Now, those are the big kind of things that we need to remember when talking about projectile motion concepts. Let's work through 6 little questions here and use this PhET simulation to kind of help us out here. So we'll go into our lab. We'll delete everything. And what we have here in question 1 is that a rock is dropped from rest. And at the same instant, a second rock is thrown horizontally from the same height, which hits the ground first. This is actually really similar to a problem we've kind of discussed a little bit in class. This is you shoot a gun horizontally and you drop a bullet at the same time. Which one hits the ground first? Well, we know that the x velocity is independent of the y velocity. And if we start thinking, what's pulling these objects to the ground, that's gravity. And they have the same amount of gravity acting on them. So in theory, they should hit at the same time. Can we prove that though? Sure. Let's take our cannon and move it up to like 15 meters, okay? And let's shoot it perfectly horizontal with a big initial speed, 30 meters per second. It's shooting fast. Fire! Ooh, that went off the screen. Let's look at the time of how long this object was in the air. It was in the air 1.7 seconds, it looks like. 1.75 seconds, okay, 1.75. Now, if we take this initial speed to 0, so that the ball's just going to fall straight down from 15 meters. Fire. Pew. See how it's just falling down? If we look at this time, we get 1.75 seconds. We have just shown once again that the x and y velocities are independent, so it doesn't matter what you get here. In the end, these objects are going to hit the ground at the same time. It's a tie. Okay, the x and y velocities are independent. Since the y velocity starts as 0 for both of them, they fall in the same way due to gravity. So that's kind of a cool thing. When we're drawing shapes for number 2 of the path of projectile without air resistance, we know that this is going to make a nice parabola. So do your best to draw a parabola there. We know with air resistance, because it's being buffeted back, we know it's going to get squished. And if we take our little cannon here, we'll set it up to like 50 degrees. We'll give it a big initial speed, and we'll say no air resistance. Fire. This thing's going to get launched out of there. A nice parabolic arc. But as soon as you put air resistance in there, we increase. Let's just make that a kind of lighter object. As soon as we increase air resistance, we're going to get kind of a squished. Okay, and we see here we don't go as far, and we get this kind of squish shape at the end. If we kind of change some masses as well, or we increase this, we can get a really squish shape like that. So that's much more squished like this. So we know with air resistance, we're going to get a shape that starts off kind of parabolic and then squish at the back end. So that's what's kind of going on there. Now, one of the kind of interesting things, and this is a sidebar about air resistance, as you change your altitude, you'll actually get less air resistance because there's less atmosphere higher up. And when you get into space, there's very, very little to no atmosphere in deep space. There's nothing there, so you get like no air resistance. One of the interesting things about air resistance as well is that it works greater on less massive, or what you would call lighter objects. So a sheet of paper, you know, not very heavy, gonna have the air resistance influence a lot. So it kind of does that flutter thing as it falls. Where if you have something like a car that you're throwing through the air, it's much more massive, so air resistance is going to influence it a lot less. So let's take a look at this real quick, and this is just kind of a tangent. Let's turn air resistance off, and then let's shoot something like a car. Okay, let's shoot a car. With air resistance off, I need to put a lot of gunpowder in my cannon to fire it, but I'm firing it at 30 meters per second, and there goes my car. Okay. So there's the car. It, you know, had a crash at the end here. But if I turn air resistance on, even if air resistance is on for it, the car is so massive that this isn't going to change very much. You notice it changes a little bit, but not that much there. Where if we change this into something else, like a custom object, if we give the mass, if we make the mass very small, we make the mass like 1. Okay, and let's make the diameter very large, so it hits a lot of air. Okay, we'll turn the diameter like 500. Oh, it's got to be something to 3. We'll make it 3. Okay, we'll keep gravity. Then what's going to happen is when air resistance is off, this object's going to shoot just like normal. Okay, it's actually going to go to the exact same spot that the Buick did. But when we turn air resistance on, it has so little mass and such a wide diameter that air resistance is going to influence it a lot. It doesn't have a lot of mass there. Look, it stopped almost immediately. Okay, here, let's change this. Let's change this to something that might be a little bit. We'll get something out of it. So it looks like initially that it's going to do the same thing, like, and then it just kind of stopped here. So the mass and diameter, when you have air resistance, they actually matter a lot. The shape of your object matters a lot. On golf balls, the little dimples you see cause the golf ball to like get some backspin and kind of like ride the air. So air resistance is really, really complicated. So like I said, we're going to ignore it. The big thing to recognize is that when you have air resistance, your parabola is going to get squished on the far edge. Okay. If we take a look at the next question. A ball is projected at a speed of 20 meters per second, and it has a range of 40 and a max height of 10. What would the range and max height be if it were projected at the same angle with a speed of 60 and then 10? Well, if we take a look at this for number 3, if we have an initial speed of 20, whenever we go 60, that's 3 times that initial speed, right? So if we go 3 times the initial speed, when we think about squaring that quantity, because we gain both x and y velocity, that's like 9 times the amount. So if we had an initial range of 40, 40 times 9 is 360. And if the maximum height was 10, 10 times 9 would give us 90. Okay? So that's how we get that. We say, hey, look, we went 3 times as fast initially because we went from 20 to 60. That's 3 times as fast. Square that 3 to get 9, and 9 times the range gives you your new range. If we do this for B, this time we slowed down. We're only going half as fast. So when we square this, well, 1 squared is 1, but 2 squared is 4. So we're going to go only 1/4 as far. So 40 times 1/4, that's like 40 over 4. That's only going to give us 10, and the max height of 10 multiplied by 1/4, or 10 over 4, is only going to give us 2.5. Okay, so that's how we think about objects as they're increasing their speed by some factor. Okay. We know for launch angles, what's going to produce the greatest range for us without air resistance? That is 45 degrees on the button. We're going out and we're going up. It's perfect. With air resistance, you just need to be something that is less than 45 degrees, okay? We don't know what it is exactly. It really depends on what your object is, where you're at throwing it, what's your object shaped like, how you're throwing it. There's no good way to predict that. You really have to run a lot of simulations or just hit a lot of golf balls or throw a lot of baseballs to get that value. We just know it's always going to be less than 45 because you need to try to go out instead of wasting time going up. Okay. If we take a look at the next one here, and let's just make this big screen. A snowball is projected at an angle of 20 degrees. It's thrown at the same speed, but it needs to be a different angle to hit the target. What angle would you choose? Well, remember, complementary angles. So 20 degrees plus something is going to equal 90, and that something there is going to be 70 for us. You may have already known this due to dodgeball in gym class. One of the common tactics that we used to use growing up was, whenever we could still play dodgeball and knock each other's teeth out, was we'd have one person lob a ball like on a big high arc so people would look up at it because that's an easy catch. I'm going to get you out. And then while they're looking up at it, we time it so that it's coming down and they're ready to catch it, that we'd bam, smack them in the head. And if you throw those objects at the same speed, these complementary angles are going to add up to 90 for that. So you've already kind of got that idea a little bit. It's a little different with a dodgeball scenario, but maybe you've done that, maybe you haven't. I don't know. And for the last one here, this one's really interesting. A projectile is to hit a target which falls from rest at the instant the projectile is fired. Where should the projectile be aimed? Now, maybe that sounds a little weird to you, how that's worded, but this is where this question comes from. It's a classical physics problem, from ages ago. And the problem goes like this. You have a hunter with a rifle. I don't know how to draw a rifle, so just bang, that's a rifle. And the hunter is trying to hunt a monkey for whatever reason. I don't know why you're trying to hunt a monkey. But the monkey's up in a tree, and here's how I draw monkeys. Ooh, ooh, ah, ah, monkey tail. Boop. When you fire the gun, though, when the hunter fires the gun, we'll give him a hat, like a, I don't know. When the hunter fires the gun, the monkey is going to fall from the tree. And you know that the bullet from the gun, it's going to, you have to aim it in such a way that it hits the monkey. Where does the hunter aim? That's the question. And it turns out that if we think about this, when you fire the gun, what is causing the bullet to arc? Well, it's gravity. What's causing the monkey to fall? Well, it's also gravity. And if both the monkey and bullet are falling in the same way, you should just aim at the monkey. And I know that sounds really weird and crazy, but check this out. Check this out, okay? This is a video from MIT where they set this up, right? They came out, they have a golf ball launcher right here, and this gentleman on the right is going to put up a monkey. So he's putting up the monkey right now, and the golf ball launcher is getting set up. So let's, there's our monkey, top right, way up there, okay? The golf ball launcher's down here. They are easily, that's 1, 2, 3, 4, easy about 20 feet apart, okay? And the monkey's up here in the tree. And all this launcher has to do is just aim at the monkey. That's it. Because as we're going to see, this projectile, the bullet, the golf ball, it's going to arc here, and the monkey's going to fall. And since gravity's doing the same thing there, you just have to aim at your target, and you will hit it. That's it. So you don't need to lead it or anything like that. Boom! Hits the monkey. Okay? So in slow-mo, we see the ball coming out, and then whack! Hits the monkey. This is a little different if you are using a bow to hunt a deer that's running, because if you're using a bow to hunt a deer that's running, you actually aren't both being influenced, the deer and the arrow, by gravity. In that case, you would have to lead the shot because the deer, I don't know how to draw a deer, so that's a deer. If the deer's running this way and your bow's going this way, or your arrow's going this way, the deer could move before your arrow gets there. They're not influenced by the same thing. So that's why, if you're hunting something moving across your vision, you do want to lead the target a little bit. You need to, account for that movement time to hit them. But if they're just falling down, just shoot directly at them. You will hit, assuming that your bullet makes it. Okay? So you simply shoot at the target. And hopefully you're not out hunting monkeys. Okay? So that just took us through a little bit more projectile ideas. Some of the things that we know about the projectiles, we can think about. And a few questions, kind of like proving those strategies, and a little demo video on how we could go out and hit something falling from a tree, or a net gun to save a monkey falling from a tree. I don't know. But these are just projectile quantities, or concepts that we should know here. And in our next video, we're going to talk about the projectile box, which will help us start to solve a lot of these problems. But for now, we are finished. Adios, and y'all take it easy.